So today, we're going to finish up chapter 12. Before I start with the new stuff, I'm going to take a moment and take questions. So at this point, I think you guys should have been working on 1 through 12. Does anybody have any questions on anything there, Victoria? Sure. So 6 says to write a linear function that satisfies the following conditions. So probably the easiest way to handle this is when I see that g of 4 is equal to 3. It basically just tells me that I need to pass through the point 4, 3. And when g of 2 has to equal 4, I have to pass through the point 2, 4. So I'm just going to do this in my calculator as a linear regression. Since I've already been doing that. Okay with that plan, Victoria? Okay, so we'll go stat. From the edit tab, we'll pick the edit command. I'm going to clear out all my stuff that I had in here previously. And then type in my X column and my Y column. I'll exit out of here now. Go back into the stat menu. This time we'll go to the calc tab. Select the linreg command. And since I'm not being asked to do anything with this equation, I'm not going to bother to store it anyways. I'm just going to display it. So here's my equation. Y equals negative 0.5x plus 5. So that's probably the easiest way to do it, since the calculator does all the heavy lifting for us. Those of you that are taking an ACT here in the future, this is a nice expedient way to get the equation for a line from points without having to actually do the process that you would have learned in like your Algebra 1 class or whatever, where you find the slope and then you plug in the point and the slope into the y equals mx plus b, and then you solve for b. This here, the calculator does it, and it doesn't make any arithmetic mistakes for you. So that's a nice option if you have an ACT coming up and you need to write the equation for a line. You can just have the calculator do it for you. Are you happy with that, Victoria? Okay. Anybody else on homework questions? Okay, well, we can always circle back if something else comes up, right? As you guys get a little further through your homework sets, we can always do that. Today, we're going to work in section 12.3, talking about other types of mathematical models. So we've already talked about in section 12.2 linear regressions. So that's basically writing a y equals mx plus b equation. And we measure the fit of our linear regressions with the correlation coefficient r. That's our measurement that we typically use. Right? And the closer that r is to either 1 or negative 1, the better fit our linear regression equation is to our scatter plot, to our data. Everybody's cool remembering that from last time? Today we're going to make mention of 5 other regressions. So I misnumbered them apparently. We have 2 number 3s. That's weird. Way to go, Mr. Kulik. Counting's hard, guys. So the first type we'll talk about is quadratic regression. So that's y equals ax squared plus bx plus c. And an instance where you'd want to use a quadratic regression is if I look at my scatter plot and it looks kind of like a horseshoe, right? It looks like a parabola. That's what we'd be looking for. Does that Feel okay? We have cubic regressions. So that's y equals ax cubed plus bx squared plus cx plus d. And the scatter plot that we'd want there should look like a cubic. So it should have like two bends in it. Right? So I give you like two different options of what that might look like. Oops. Oh, I wrote that wrong. So our exponential would look like AB to the x. And what our scatter plot there should look like is kind of flat and then getting very vertical. And then our last one is logarithmic, which starts very vertical and then kind of starts flattening out. Now, these first four that we've shown you guys, these are all function types that we spent a good amount of time in talking about last year in our Algebra 2 courses. Right? We should have spent a good amount of time talking about quadratic and cubic and exponential and logarithmic functions. So we should have some memory of what those graphs kind of look like. Is that ringing a little bit of a bell? And if not, we just redrew them and it's just kind of remembering what they look like. And then our last one is this power model. So this is kind of the new one. This is ax to the b. And you might say, looking at that, be like, Mr. Kulik, that looks a lot like a polynomial, right? Like what's different from this thing than a polynomial? Well, what's different is that that exponent can be any kind of real number. It doesn't have to be a positive whole number. It could be negative, it could be decimal, it could be fractional, it could be all kinds of kooky things. And a power model is nice because it's rather versatile. It can kind of fit any kind of shape. It may not always be the best fit, but it's usually not a terrible fit either. Now, when we talked about how good of a fit a linear regression was, we used that correlation coefficient, that value for R. When we talk about how good of a fit any of these other nonlinear models are, the quadratic, the cubic, the exponential, the logarithmic, or the power, we use what's called the coefficient of determination. That's the R squared. You notice that that's come up when we've done our regressions also. And as that R squared value gets closer to 1, the better the fit is. Obviously, since R is squared here, it has to be a positive number, so it can't be negative. So the R squared value is stuck between 0 and 1. 1 is a perfect fit. 0 is absolutely no fit. The closer to 1 you get, the better fit you have. So it's, if I'm comparing two of these different models and trying to decide which one is the better model to use, I can just compare the R squared values, right? And whichever one has the bigger R squared value would be the better model. Does that make sense? Okay. So I want to take a few minutes here and talk a little bit about this power function. Because that's something we didn't spend a lot of time or any time in our Algebra 2 class talking about, and I want to do a little bit of vocab and a little bit of work with that before we move on. The other ones are things that we did spend a lot of time in our Algebra 2 class, and I hope that we have some memory a little bit more so of these guys, but the power function I know we didn't really spend any time with. So let's talk a little bit more about that. So when we talk about this power function, the exponent b is called the power, and the coefficient a is called the constant of variation or the constant of proportion. Kind of might be called different things in different textbooks. I think that I remember it as the constant of variation. When I did this, I think that's the same reference in your book pages that are in your the lessons or whatever. I think that's the same vocab we use there. So let's take a look here at some examples. So here's a bunch of different functions that could all be considered power functions. And we're just going to identify like the power and the constant of variation for each of these. So the first one here is describing the circumference of a circle. And we see that the circumference of a circle varies with the radius. As the radius gets bigger, the circumference gets bigger. So here our independent variable is r, and our dependent variable is c. Everybody agree with that? Okay. So the power is the exponent on the independent variable. In this case, that value would be for a power function, the power is the exponent on the independent variable. What's the independent variable here? You just said it. Any pirates in the room? R. What is the exponent on R? 1, right? We know there's a 1 there, even though we didn't write it. And then our constant of variation is the coefficient. In this case, what's the coefficient on our independent variable? Close, 2 pi, right? Both of those are constants. Cool, so far so good? Okay. Maybe I'll write pow. I think I have a P in one of these upcoming ones. So the next one is the area of a circle. We know the area of the circle varies with the square of the radius. So again, what's our independent variable here? R. And what's our dependent variable? A. Okay, what's the power then? 2. That's the exponent on the independent variable. And what's our constant of variation? Pi. Okay. Current or former chemistry students may recognize the next one. We know that the volume of an enclosed gas at a constant temperature varies inversely with applied pressure. You guys remember that one? I think that's Boyle's law. That might ring a bell. Do gas laws in chemistry? Yeah, I think you should have. PV equals nRT. Yeah, Jack says I did it.
Well, I actually didn't know that. We called it.
Of course. PivNerd or something, right?
Yeah.
Yeah. So here, if volume is varying inversely with pressure, which one is the independent variable? Pressure. Very good. And the dependent variable is volume. Okay. So what is the power then for this power function? It's actually not 1. It's what? Did you say K? It's not K, and it's not 0. We could also rewrite this way, right, with a negative exponent on the P. Remember, a negative exponent makes a reciprocal. So what is the power really here? -1. Mr. Kulik, you're so sneaky. Yup. You never underestimate the sneakiness on your math teacher. And then the constant of variation. Okay. Yeah. Okay. We'll do one more. This next one is the volume of a sphere. Varies with the cube of the radius. Our independent variable is r. Our dependent variable is v. So our power is 3. And our constant of variation would be 4/3 pi. Everybody okay? Not too difficult. It's just kind of like using the vocab. Maybe you have to pull out like an algebra rule like we did on number C there to figure out what the power was because it was kind of hidden from you, but by and large it's, it's not really complicated. Let's look at a situation where I give you the power function in words and we're asked to write the power function equation. So here it says, write a power function for the given scenario. An object is dropped off a building. Its distance from the ground varies with the square of the amount of time it's been falling. So distance is varying with time, right? Everybody pick that out of there. So what is my independent variable going to be here? Time. And our dependent variable is? Okay. So I know I'm going to have d is equal to something t, right? What else do you notice in here? Okay, the power is 2 because we have the square of the amount of time. Okay, and are we given a specific about what the constant of variation is here? So what should we write? Just call it K or A or B or something. Just give it a name. Physics students. Anybody currently in physics right now or has been in physics? What's K in this situation? Negative 9.8 meters per second squared. It's the gravitational constant. Because it's just you're dropping something off a building. What? I know we don't call it K. But you'd use G, right? Yeah. I just picked K for constant because that's what we used way back in when we did the model originally. But it doesn't matter what letter you want to give it. But that's what that constant of variation would represent in this case. Or if you're in the English system, what is it, like -16 or something? Is ish. Okay. Last example here. So it says, given the data table, use the data to create a scatter plot and create a power regression curve to model the data. then use that curve to estimate the orbital period of Neptune, which is 4,497 gigameters from the sun. Well, okay. So I'm going to start by entering this data into my calculator. So I'm going to press the Stat button. From the Edit tab, I'm going to select the Edit command. I'm going to clear out L1 and enter in the distances from the sun there. And just as I do this, I'm going to talk a little bit. I am pretty sure that the distance from the sun should be my independent variable. Because if I think about planets, I know they orbit the sun in elliptical orbits. The farther that distance from the sun, that's like the radius of the thing. That's going to make a bigger orbit, and it's going to take longer to do it. So it certainly seems like the length of time it takes to orbit the sun should be dependent on how far away from the sun it is, because it has a bigger circle to travel. Now, I know that the planets don't really travel in circles. They travel in ellipses, but it's close enough. So the orbital period there is just the length of a year, basically, right? How many days would be in a year? So notice on Earth, the orbital period there is not surprisingly 365.2. What's the 0.2? That's the little leftover that becomes a leap year, right? Every 5 years you get an extra day in February to account for those 0.2s that add up to make an extra day every 5 years. Is that cool? Okay. So I got all my data in. We've decided that the distance is my independent variable, so those are like my x's. Since they've told me to use a power regression, I'm not going to bother to create a scatter plot because I already know what to use. If I wasn't sure what to use, I would want to look at the scatter plot to make a decision, but I'm not going to bother with it in this case. So I exited out of the lists. I pressed the Stat button again, but this time I'm going over to the Calc menu. I'm going to scroll down till I find the power regression. PWR is for power regression. PSLN reg is the logarithmic regression, just FYI. So again, my x's were in L1, my y's were in L2. We never used the frequency list. Since it is going to ask me some question about using my power model, I'm going to store this because I'm going to need to use it to answer the rest of the question about the orbital period for Neptune. So where we're going to store this is going to be into Y1. To get the Y1 to show there, I'm going to press the vars button. Var is short for variables. So I'm going to find the Y1 variable. Since it's a Y variable, I'm going to go to the YVars tab. Since our calculator is in function mode, and will always be in function mode in this class, I'm going to pick the function command, and there's Y1. And then I'll hit calculate. So here's my power regression. So it's y equals 0.2-ish x to the 1.5-ish. Everybody's okay with that? If I look at that r squared value, it's quite good. That's awful darn close to 1. So pretty excellent fit. Everybody's cool? So that's my power regression curve. That's the first part, right? I guess we didn't create the scatter plot because I skipped it, but whatever. There's my curve. And then to estimate the orbital period of Neptune, I basically need to plug 4,497 in for x. The easiest way to do this, since I've put this into my Y1 menu, is to do Y1 of 4,497. So I'm going to go and retrieve the Y1 variable again. So I'm going to press vars, over to the YVars tab, select the function option, and then select y1 from the list, and then I'll put the parenthesis. So I'm basically doing like a function notation here, like I'm doing f of 3. This is like y1 of 4,497. Wowzer! 60,150. That's a whole lot of, it's a long time. To put that in comparison, if the orbital period for Earth is 365.2, it's basically 164 years is one orbit of Neptune. Not a lot of probably Neptunians get to celebrate their first birthday, huh? Anyways, essentially all the problems here in section 3, the work that you're doing on your calculator is exactly the same as what we did in section 2. Right, you're just using different models from the list, but like everything kind of works the same. And by and large, the problem will tell you which model to use. If it doesn't tell you the model to use, that's when you really would want to look at the scatter plot and look at the shape of the data to make a good decision. And if you're like, oh, boy, that could be exponential, or maybe it could be quadratic because we just have like part of a curve, do both of them and take the one with the better r-squared value, you know? Yes, Victoria. Closer to 1. Yep. Yep. So again, we said that these r-squared values, as r-squared gets closer to 1, the better the fit. So that's the piece that you can compare two of these models to be like, oh, I don't know which one would be better. R-squared makes it really easy, right? If you graph both of them, it's like, I don't know, they both look pretty good. It could be tough to tell if they're both pretty good. So that's it with chapter 12. We finished. What? So next time is like our review day. Guess what else we're going to do next time?
Watch a movie.
Not watching a movie. But we might do something else that we do every chapter that we haven't done yet.
A homework quiz?
Yeah, what do you suppose you're going to definitely want to have with you?
Some popcorn to watch the movie.
You definitely want your calculator, right? And your popcorn, for sure. And with your calculator, you definitely want to be able to make like regression equations and use your regression equations with your calculator. So if you haven't practiced that yet, I would advise like definitely do some of the problems where you're doing that to practice that. Everybody cool? The homework quiz is really going to just be up through like 1 through 7 is really kind of the homework we're pulling from. I wouldn't have any of the new stuff on there, although it's not really different from a step standpoint on your calculator than anything you've done yet. Landon?
Are we going to get a half sheet of paper for this next quiz or test?
Yeah, we'll talk about that probably on that day in class. I haven't really decided because I didn't even make a review for this because I don't know why I don't have one already made, and I sat down, I looked at them like, I did write out like the test format, and I suppose there's no reason that you can't have a half sheet of paper. If anything else, probably the calculator steps would be what you'd probably put on it. Yeah, which doesn't seem unreasonable. We'll deal with that though on Friday would be the day that we would deal with that, assuming we have school, and if not, we'll deal with it when we come back. Just FYI, when we come back from break, I'm going to start chapter 13 and maybe take a couple of review questions from 12, and then the following class will have the test, so we're not taking the test the day you guys get back from break, which feels like kind of a crummy deal. So just don't let that get too far away from you over break, but you will have a chance to kind of get recaught back up around it. Of course. All right. I'm done with you guys.